picture a curtain. The bottom edge follows a wiggly path on the floor, while the top edge follows a wiggly surface above it, rising and falling however high that surface is at each point. The line integral we're about to build is simply the area of that curtain. If the path only moves in the x direction, or only in the y direction, this is just a normal single variable integral, nothing new. But if the path bends in both directions at once, we need a new method, the line integral. Before we touch any line integral, the curve must first be written using a single variable, t. Think of t as time. As t ticks forward, an imaginary point walks along the curve, tracing it out. So step 1, always, is to parametrize the curve. We write r of t equals x of t times I plus y of t times j. Now picture chopping the curve into many tiny straight pieces. Each tiny piece has a small length, which we call d's. Above each tiny piece of curve stands a thin flap of curtain, and its height is the value of f at that point, f of x and y. Add up all of these tiny flaps, all along the curve. As the pieces get infinitely thin, this sum becomes the line integral. A Riemann sum, just like ordinary integration, except now the width being summed is a piece of curve, not a piece of the x-axis. Now we need to actually find ds. Picture a tiny right-angled triangle sitting right on the curve. One leg of this triangle is a tiny step in x, which we call dx. The other leg of the triangle is a tiny step in y, which we call di. And the diagonal, the piece hugging the curve itself, is exactly ds. So ds equals the square root of dx squared plus di squared. This is nothing more than Pythagoras' theorem applied to a tiny triangle. Now, once the curve is parametrized as x of t and y of t, we can rewrite dx as x prime of t dt and di as y prime of t dt. Substituting these into ds turns the whole line integral into an ordinary single variable integral in t. This gives us the master formula. The integral over c of f of x, y, ds equals the integral from t equals a to t equals b of f of x of t y of t times the square root of dx dt squared plus di dt squared dt. Every line integral you compute will follow exactly this pattern.